Drop a chunk of this highly reactive metal into a pool of water, and it violently detonates. Yet this same family allows us to measure time with enough precision to synchronize global GPS networks. These are the alkali metals. They occupy Group 1 of the periodic table, a vertical column beginning with lithium and ending with francium. Their roles vary significantly, powering our smartphones, regulating human heartbeats, and ticking inside atomic clocks. This range of applications follows the mathematical constraints of the group's shared quantum mechanics. To see how these elements drive modern technology, we have to look at their shared subatomic architecture. Group 1 elements share the NS1 configuration, a single s orbital electron far from the nucleus. Its distant, weak binding energy means it's easily stripped away, causing high reactivity. Moving down the table, each new element adds a principal quantum shell under this outer electron. These inner layers create electron shielding. This dampens the effective nuclear charge, reducing the actual attractive force that reaches the outermost electron. Tracking how this shielding increases from lithium down to francium provides the key to predicting the engineering potential of each element. Lithium, element 3, is extracted primarily from terrestrial brine pools and pegmatite minerals. At the top of the group, lithium has the lowest mass and smallest atomic radius. With only one inner electron shell, it has minimal shielding. The nucleus grips the valence electron tightly, resulting in the highest ionization energy. This combination of low mass and a small radius gives lithium the highest charge-to-weight ratio of any solid element. This ratio allows lithium to pack more energy into a smaller footprint than other metals, making it the primary choice for mobile energy storage. This microscopic compactness enables the high-capacity batteries found in electric vehicles and portable electronics. Moving down the table to sodium and potassium, we find elements mined from halite and ancient marine potash deposits. These elements have additional electron shells, which increase their atomic radii. Their lower ionization energy makes them reactive enough to aggressively displace hydrogen from water. Terrestrial biology exploits this reactivity. Because sodium and potassium have moderate ionization energies, they readily lose their valence electron to become ions when dissolved in the aqueous environment of a cell. The sodium-potassium pump uses these ions to regulate electrical potential across cell membranes. While both form 1+ ions, they have distinct physical sizes. The pump uses these differing ionic radii as mechanical keys, selectively moving sodium out and potassium in. This continuous exchange creates the electrochemical gradient that powers every heartbeat and nerve impulse. On a macro scale, potassium's high solubility and role in plant metabolism make it a critical component of global agricultural fertilizers. Human biology and agriculture depend on the specific nuclear charge and physical size of elements 11 and 19. Rubidium and cesium are rarer elements, typically mined as byproducts of lepidolite and pollucite ores. In a cesium atom, dense inner electron shells heavily shield the nucleus from the lone valence electron. This extreme shielding creates an incredibly low ionization energy. The valence electron is so loosely bound that its orbit becomes highly unstable and easily displaced. This looseness allows for extreme precision in quantum measurements. Because the valence electron is so loosely held, it can be easily excited to transition between energy states, oscillating at a perfectly consistent frequency. This oscillation is the core of an atomic clock. The modern second is defined by counting exactly 9,192,631,770 of these cycles in a cesium atom. This standard of time is required to synchronize global GPS networks and international data grids. The synchronization of the digital world depends on the weak electron binding found at the bottom of Group 1. Francium, element 87, has almost no natural abundance on Earth. It's primarily produced synthetically in particle accelerators or captured during the radioactive decay of actinium. It represents the atomic limit of the group, possessing the highest mass, largest radius, and lowest ionization energy. With a half-life of only 22 minutes, it decays too quickly for any commercial or biological use. Its value is purely theoretical, serving as a laboratory for physicists studying the weak nuclear force. Plotting ionization energy and atomic radius against atomic number shows how periodic law translates properties into industrial utility.
Lithium's tight radius provides energy density for batteries.
Sodium and potassium's reactivity and sizes enable nervous system signals. Cesium's loose electron binding allows precise time measurement. While the NS1 valence electron makes these elements reactive, it is the internal electron shielding that determines their specific use. The alkali metals show how understanding subatomic architecture allows us to build the materials that power and synchronize modern civilization.